All right, guys. It's 7:06 right now, U.S. Central Time. So let's get a training started, so we don't stretch it too late. I'm sure everyone has a busy day tomorrow. So for all of you join the training live, first of all, I want to appreciate your time and effort to make to the training. I'm sure after a long day of work, you guys got a lot of other things that you can do, a lot more fun things like, lying on the couch drinking beer, watching whatever you like to watch. So again, thanks for joining the training, listening to me talking about boring data, and all the technical findings from our study. So hopefully, in the next 2 hours, you will find the information you learned to be fairly useful for your future operation. All right, my name is Steve Lee. I'm the extension specialist and associate professor in College of Agriculture of Auburn University. I'm a weed scientist by training, but many of y'all know I do a lot of work with spray drone, precision spot spraying, variable rate, and all kinds of application related projects these days. My focus is mainly on the chemical efficacy and application assessment. So it is mainly from my agronomic background. So I'm not an engineer by training. I cannot answer questions really, as well as compared to the engineers, like Mark. This is why I got him in the Q&A section with me. So we try to cover as many aspects as we can. All right, let's get the training started. Just a very brief introduction and background about U.S. corn production. Um, as many of y'all know, corn is the largest crop in the country. So basically, we're looking at over 90 million acres. I don't have the latest data. Well, I really didn't look, I'll be honest, from USDA this year. There could be some up and downs, but typically we got lots of corn in the country. Um, Decent amount of the corn acreage gets at least one shot of fungicide every year. USDA estimates 15.1 million acres. This number seems to be a little bit lower, a little bit low to me, especially after Midwest has this new disease called tar spot. So potentially the number could be higher. Yield loss was estimated to be 3.6%, according to someone's study. I don't really know how they come up with the number, but as everyone knows, it just depends on the year, depends on the environmental condition, rainfall, all of those. If you have perfect condition, conducive for the disease, you could have a lot, which cause significant yield loss. But, very dry summer, you may have a hard time to find any type of corn disease. Typically, the application method is area application. And in this study, they found fungicide application did not affect yield of corn in 7 of the 9 site years on farm and small plot trials in Iowa. I probably would believe it. It's more of a preventative application instead of curing the disease after your corn is eaten up by corn rust, or tar spot, or northern leaf blight, that kind of thing. So most of the time, you may not see a positive yield response, but if you do not spray your crop and then get ate up by the disease, you could lose a lot of the yield. That'll pay a lot of fungicide for many years in a hurry. Ground sprayer typically provided better application uniformity than area application. That was from this paper just got published last year. My data somewhat agreed with this finding. Ground rig, particularly at a 15 gallon per acre, provides better uniformity, although they damaged the crop as well, the physical damage. And also after fungicide treatment, the percent of lodged plants was less. That's not difficult to understand because the fungicide increased the stalk strength, so it is more resistant to lodging. All right, here is a quick overview of the training content. So I'm going to go over the 2022 data first because we spent quite a bit of time in the field since last year to do the corn fungicide application and application study. And then I'm going to cover the study results from this year's trial because we spent a lot of time again this year in the field to get this trial done. This is literally the biggest project for us in the last 2 years. And then my friend, Dr. Jason DeVore, he actually cannot join the training live with us today. So he recorded his presentation, and I'm going to play the video recording, to show his study. And Mark is also the co-author of this study. He will answer any of the questions related to that study. That's also what we're going to do at the Q&A session, basically answer any questions related to the studies and also answer any type of questions related to corn fungicide application as best as we can. All right, that's a quick overview of the training content for tonight. Hopefully we'll be done around 9 o'clock, because like I said, everybody's busy. You probably got plenty of things to do tomorrow. All right, so a quick overview of the 2022 study with the T30. We want to evaluate different application methods for deposition and uniformity. And also, we want to also answer the question, does DRA make a difference on deposition? And also, what about spray variation? Not just the variations among the plane, but also the variation among all the application equipment. So we sprayed with plane. We hired a crop duster, spray with plane. We spray with T30. We also spray with a ground rig. As you can see, nobody preferred this method because we saw lots of physical damage there. And high boy can barely, stay on top of the crop. And the grower said, for one pass, I'm going to do it for you. But if you want me to spray with a ground rig over the whole field, no, that's not going to happen. It's too much damage on the tassel corn over there. All right, so here is a quick overview of all the treatments that we used last year. The drone was sprayed all with T30. We didn't really use a very wide swath just because as a research study, we don't want to stretch the equipment to the limit. Last year, this was the first year we run. That was the first year we run large-scale trials with T30, so we were a little conservative with the setting. And this year's study, we did use 25 feet for the T30, so you get to see 15 feet, 20 feet, and 25 feet swaths with data using those different swath widths. So we use airplane, we use a drone, we use two different type of DRAs. We use air mix 110-01 nozzle just because our swath is real narrow, so the flow rate is fairly low, so I have to use 01 nozzle to give me a decent amount of coverage. And also the height could be either 8 feet or 12 feet. For airplane was roughly around 10 feet. And also we use a ground sprayer as well. Ground sprayer sprayed at 15 GPA, airplane and the T30 sprayed at 2 GPA. All right, you can come back and look at all these treatment settings later when you watch the recording. All right, weather data. The most important thing for us is the wind speed. Wind direction maybe a little bit, but wind direction is really not something we can control, just as wind speed. So it is what it is. In last year's trial, we tried to avoid high windy condition as best as we can. All right, so as you can tell from the number, there was not much wind at all. The largest wind we had was a 3.4 mile per hour, and that's like a nothing. All right. This year is really windy down here. Typically in the southeast, particularly like us in the deep south, we don't have much wind in summer. If it's a hot, humid day, typically it's as dead as it can be. 2 o'clock in the afternoon, you look at the tree leaves, it's not even shaking at all. It's pretty dead. This summer has been very different. It could be 9 o'clock in the morning. I'm seeing already a lot of wind coming, all over the place. So it has been way more windier than in the past. So that's the difference between last year and this year's trial. You will be able to see this difference in the wind speed data we collected when we were spraying the applications, right? So last year we sprayed the fluorescence rhodamine dye over the top of corn, and then the concentration we used was higher than this year's concentration. We realized from last year's trial that we didn't have to use this much dye because we use a lot of dye. We literally not bleach. We literally paint the corn leaf from green to pink. That's how much dye we got on that leaves. That's way too much for us to analyze. It actually causing some headache during the extraction and analysis process because we have to dilute this pink juice several times so we can use our instrument to analyze, because the instrument is too sensitive. If you overload the instrument with too much dye, it's going to affect your results as well. So we have to do a lot of dilution last year. So this year we didn't clip the whole leaf, so we improved the methodology. This year we use smaller plastic malacards and the water sensitive paper. So we're actually collecting more data using a more efficient way. But this is how we collected data last year. In 2022, we collected the year leaf and also the third leaf above the year leaf. So that's what we call low leaf and higher leaf, or upper leaf. Upper leaf is this leaf, the first fully expanded leaf, here. And then the year leaf is basically the one right next to the ear. That's why it's called year leaf. But protecting year leaf with fungicide is very important because year leaf contributes 20 to 30% of the yield, because that's the leaf closest to the cob. All right. Look at our spray block. So for drone blocks, we use 250 long, 150 wide area. So this is what we call a drone block or treatment block. So in the treatment block, we had 3 transects. So what does transect mean? Transect means 25 marked corn plants, in a row. So corn row direction and drone fly direction go north and south, for example. And then the transect go east and west, perpendicular to the fly direction. And then each transect has 25 plants marked. All right, so basically 25 rows, 25 plants. So each row goes north and south, north and south, north and south. We basically pick 25 plants on 25 rows. This is this is in the middle of the block, typically. And then the drone block was at 150 feet wide. So this literally covered 50 rows of corn. Down here in this field, corn row spacing was 36 inches or 3 feet. So the width of the block was 50 rows, and we sampled the 25 rows at a different position inside the plot, on the right, in the middle, and on the left. But each transect was 25 rows wide or 75 feet wide. All right, that's how we did a replication within the block. And after we harvest the pink corn leaf, we shook them in a food container using distilled water. So we washed the dye off. And then my grad student, PhD student, Livia, and other student helpers analyzed the dye in the lab using the fluorimeter. This one is very sensitive. It can detect as low as 1 parts per billion of the dye, in the solution. So this treatment actually looks really, really good. This is super consistent, in my opinion. I don't know which treatment this is, but if you look at each of this cuvette, each of this little cubic container or cubic sample container is 1 corn leaf that has a dye extracted from 1 corn leaf. You can tell the uniformity of this treatment was fairly good. Not all treatment look like this. I'll show you some horrible ones. You can realize the variation of the dye on these corn leaves. All right, with DRA, we seem to see a little deeper or darker color versus without a DRA. So that's what we try to tell people. DRA helps you increase your deposition. That's what deposition means. So we're basically visualizing the deposition. All right. We had 3 sites last year, so I want to bring out the Blakely, Georgia site. This site has a 36-inch corn, fairly thick canopy, and also we had a ground sprayer here. You saw the video earlier. Ground sprayer sprayed 15 gallon per acre. T30 and airplane sprayed at 2 GPA. All right, we have 2 color of bars. Red color bars represent the dye concentration, the spray dye concentration on the year leaf. The gray color represents the dye concentration on the upper leaf, the third leaf above the year leaf. All right, so we'll focus on the year leaf first because that's the most important thing we're trying to protect. Statistically speaking, you can see all of the red bars got A, red uppercase A letter. That means statistically there are no difference here. They're all the same. Okay, whether I flew the T30 high, a little lower, little wider swath, or a little narrower swath, it didn't make a difference. And also compared to the airplane and the ground sprayer, it was the same. It was the same. On the upper leaf, we saw more variation. For 2 treatments, we saw more deposition, higher concentration with upper leaf compared to year leaf. But with some treatment, we saw, kind of similar results, between the upper leaf and the year leaf. For example, ground sprayer and also this drone treatment, there's not that much difference between the upper leaf and year leaf. If the upper leaf retain more dye than the year leaf, I wouldn't be totally surprised because they're closer to the nozzles, as you would imagine. So this was Georgia site's results. And also from Blakely, Georgia site, now we're looking at a CV, coefficient of variation. So this one basically measured the uniformity of spray dye on the upper leaf and the year leaf. The lower the CV means the lower the variation is. So lower CV typically means higher uniformity. So as you can see, ground rig has a fairly good uniformity, particularly at the upper leaf. On the year leaf, it's a little bit higher, it's around 60% variation. All right. For the spray drones, particularly on year leaf, they were higher than the ground rig. So this is why I say I generally agree every application is going to create more variation, coverage variation than the ground rig. It's just because ground rig sprays 7.5 times more water than the airplane or the drones. On upper leaves, it's kind of up and down a little bit, but generally speaking, we say for area applications, you're basically looking at anywhere between 60 to even 90% variation, in terms of CV. That's based on the sample we measured on the plants. If you do this type of measurement on the flat ground, using petri dishes and whatever on the flat ground without a crop, you probably will observe lower CV. So Mark's company makes a really cool instrument called a swath gobbler. I just got one not long ago. It's hate to admit, Mark's still in the box. We don't have time to play with it until probably later in the fall after we slow down a little bit. If you measure the coverage using swath gobbler, probably you will see lower CV, more uniform deposition. That's because on flat piece of paper versus on real plants, we're talking about different things. That's an apple to pear type of orange, or to orange type of comparison. So these things are not quite similar to each other. All right, this is why the variation looks a little higher on my samples versus on some string results, or flat surface testing. All right, so apologize for the graph look a little bit different. This was from last year Talladega County, Alabama site results from, we just didn't have enough time to make new graphs to show the data. So we don't have an airplane here that we can use. So we just have to use a ground sprayer. I mean, the farmer has a really high boy. So he used his high boy to spray corn in any way. And also his corn is on 20-inch row. So it's very narrow. It's very narrow. that probably has changed the canopy a little bit. As you can imagine, 20-inch corn might get a little thicker than the 36-inch corn. So again, we're looking at the dye concentration on the high leaf, which is upper leaf, and also on the ear leaf. Ear leaf is that's represented by the red bars. So if we look at the concentration on both upper leaf and the ear leaf, but for both leaves, the concentrations are significantly lower compared to the T30 treatments, and particularly on the ear leaf. You see the letter is B, and also the letter is A. You see a bunch of red A's. That means for ear leaves, all 4 drone treatments produce significantly higher spray dye concentration on the ear leaf. For upper leaf, it's the same thing. This one was the lowest. That's why I got a D. This one is statistically similar as the ground rig. But for this one, and this one, they were statistically higher than the ground rig, even at the upper leaf. I think the difference between this side and the Georgia side was because the row spacing. Corn here is on a narrow row, so they probably overlap and to cover the ground a little bit more efficient than the wider row. So there's not a lot of gap between the plants, between the rows and the leaves for the dye to go through. So that's why even the ground sprayer struggle. But with drone, you get a little bit propeller downwash, helps kind of push the dye into the canopy. That's my explanation. Again, I could be wrong. Looking at the uniformity, like we said, ground sprayer typically gets you the best results. Again, if you look at the 2 bars here, for the higher leaf and lower leaf or ear leaf, yes, ground rig has the lowest CV, which means the lowest variation. However, that doesn't always mean drone cannot do a good job. If you look at the drone using 15 feet swath and 12 feet altitude, so it's to fly a little higher using narrow swath, it's literally the same. It's the same as the ground sprayer. So we can spray uniformly with the drone, but you have to narrow your swath a little bit, fly a little higher, and also look for a no wind condition, because wind can screw up uniformity really fast. Go back a few slides. All right. If you look at here, ground sprayer, this is the Georgia side as dye uniformity data. Ground sprayer's uniformity was around 50 to a little over 60% variation. This treatment, again, T30 flew at a 12 feet high, 15 feet swath, had almost the same uniformity. Sorry, the same uniformity. Don't know what I hit, my bad. This one had almost the same uniformity compared to the ground rig. Again, we saw this 2 times in a row. If you really set your drone to be very precise, a high quality setting, and also you watch for the wind, we can spray as uniform as a ground rig, but that doesn't always happen. I'm sure not a lot of commercial operator wants to shrink the swath from 25 feet down to 15 feet. Although that is a better way, to get more uniform coverage. All right, there we go. Looking at the DRA effect. So what is a DRA? DRA means drift reducing agent. All right, drift reducing agent not only reduce driftable fines, it also helps you increase the coverage and the deposition of the chemicals. All right, that's the other function. We're looking at drone without DRA. That's basically just straight water. All right. And then this one is the dye concentration on the upper leaf. And then this one shows the dye concentration on the ear leaf. That's what we saw at Alabama site. This is a site close by Auburn, about 40 minutes. With DRA, it seems that the upper leaf dye concentration decreased a little bit, but we saw a trend of increasing dye concentration on the ear leaf, which is more important. That means more dye gets deeper into the canopy versus water only. Unfortunately, last year, we did not have a statistical difference. This is not statistically different here, with comparing the dye, comparing DRA to the water. So I said this last year, My goal for 2023 field trial is I want to have a few DRA treatment produce significantly higher dye concentration on the year leaf versus water alone on year leaf. And I was able to do it, I'm going to cover those data just in a minute. So this year we were able to use DRA to create significant higher concentration of dye on the year leaf versus water only. All right, looking at uniformity. Again, lots of variations. Every application has never been super consistent. Drone without DRA, airplane without DRA, we're still in this 60 to 90% range, over here. With DRA, we saw a little bit lower variation. We're below 60%, particularly with this DRA2, which is the experimental compound that we tested last year. I can tell you DRA1 is interlock, Winfield's DRA. So we saw more uniformity with DRA last year, which is a good thing. All right, so quick summary of the 2022 study. I have to finish the 2022 before I can move on to 2023. T30 airplane and a ground rig produce similar dye concentration and spray uniformity at the Blakely, Georgia site. T30 produced higher dye concentration on year leaf and upper leaf at the Talladega site versus the ground rig. I should write this bullet point a little better. This is the drone versus ground rig comparison. Fluorescent dye concentration on the upper leaves has the tendency to be a little higher than year leaves, but not always. Sometimes that's not the case. I can only describe the general trend. Using T30, we saw 15 feet swath, 12 feet high, produced the lowest CV, which means the lowest variation, and the highest uniformity among all the drone treatments, which has different combination of the parameters. DRA also showed a trend to increase year leaf dye concentration and reduce the dye variation, but it was not statistically significant. So that's why I say we only saw a trend. That's how we can describe it. All right, folks, if you have any questions, you're welcome to type your question in the chat box at any minute before you forget, because we're going to cover a lot of data today. Guarantee you'll be kind of brain dead at the end of the training, but that's fine. That's why we have recordings. You can always go back and watch recordings. All right, now we turn the page. Here we come, 2023. The effort continued thanks to our wheat and feed grain, commission. So they used the checkoff dollar to continue support this type of research trials this year. So to build on what we know and what we learned from last year, we tweak the study objectives a little bit for this year's project. The most important thing we still want to hammer is the comparison between spray drone models to airplane. We want to see if these two type of application equipment can produce apple-to-apple type of results, which means they are fairly similar to each other. Or maybe one is better than the other, who knows. The second objective was to continue the effort of drift reducing agent or DRA evaluation to elucidate their effect on dye deposition and spray uniformity. And also this year, we added objective. So we want to evaluate 2 versus 3 GPA, because this is a common question from the operator. Many folks have asked me a similar question. This is one of it, one of the common FAQ. Should I use 2 or should I use 3? When I spray my corn fungicide, I want to do a good job and impress my client. We can discuss this a little bit at the end of the training. And also, how does a fly direction affect your spray quality and deposition? Should you fly along the rows of the corn, or should you fly at an angle, or should you fly across the rows at a 90 degrees angle, or what's the best? The last thing we want to evaluate is to characterize the canopy penetration a little bit better with airplane and drone application. What I mean by canopy penetration is sampling more leaves to describe this vertical penetration process a little bit better. So that was the 4 objectives. As you would imagine, we expand our operation. So this project actually got bigger than 2022. Now we got more treatments. I'm going to slow down for a minute to give you guys some time to go over the information on this page. I know it looks a little busy. We got a lot of stuff going on here. So we conducted the field trials at 2 locations, Henry County, nearby Alabama and Georgia line, and still use the same field in Early County. That's the Blakely, Georgia site from the 2022 study. We literally use the same field because that's a high yielding cornfield under irrigation, 250 bushel yield, very difficult to find down here in the South. Both fields are actually under irrigation, high yielding field. Yield is somewhere between 250 bushel. So we can guarantee the results are credible, because we use good cornfield, not some crappy dryland field, about to die in middle of July because of drought stress. And also this year, we used our new friend Agras T40 along with T30. The main focus is on T40 because I do like the rotary atomizer, the spinning disc, way better than 16 hydraulic nozzles. I can tell you because we have really sandy soil down here. Every time the T30 take off, it's a dust storm. It's just messy. The dust gets picked up by the nozzle easily. So as a result, as a consequence, I have clogged nozzles all the time. Doesn't matter which type I use, XR, TT, AIXR, or air mix, you name it. The orifice get clogged up by the dust all the time. It's almost like we have to inspect the nozzles multiple times every day before we take off, because there's always some nozzle spinning water, with a funky pattern, or only spin the pattern on one side, the other side just doesn't have anything. So that's a major problem for us with the hydraulic nozzle drones. So that's why I say T40 was better. And also, my grad student was spraying with T30 and T40 this morning, spraying peanut fungicide. Again, some fungicides get thick, so he sprayed a 2-way mix fungicide with boron foliar because peanut needs a lot of boron if you want to have healthy pots in the ground. So with I think it's a convoy fungicide, Bravo Silk fungicide, and the boron tank mix this morning at 2 GPA. He called me when I was in Mississippi this morning, and he said, I can spray with T40 fine. T30, no, that pump basically gonna give up. It's too thick for the T30. So that's the other reason why I kind of like T40 better. So the treatments highly favor T40 in this year's trial. So we basically only had one T30 treatment. All right, so we had high efficiency setting, which means 2 GPA, fly as fast as we can using real wide swaths, 32 to 33 feet, and a 10 feet height. A lot of people ask me, how high should I fly? Most of the time, my answer is it depends on the terrain. If this is a carpet flat field, 10 feet is fine. You don't have to fly higher. But if you got some elevation change, rolling hills, you got to do minimum 12 to 13 feet, to avoid collision radar does funky things for you, because I've seen so many times T40 gets slow down or completely shut down and just slam on the brake and stop in front of a hill. T40's height control is less than ideal. Let's put it that way. I think it's actually pretty terrible in a lot of cases. This new firmware drama, the one they rolled out, took it back and rolled out again, and that firmware drama that DJI is having right now, one major complaint is the height control. It does some funky thing or crazy things in the field. We have observed it several times, just in the middle of the field, the drone stopped for no reason. There's no obstacle, not even much terrain change, But it is what it is. None of the technology can be perfect without improvement. So just hopefully they find a fix for it. Um, so we use high efficiency setting and high quality setting, which is the 3 GPA setting with narrower swath, 30 feet per second speed versus T30, 2 GPA, 25 feet swath. I made it wide. Flew at top speed, 23 feet per second, same height, using XR 110.15 miles. All right, all the rest were interesting treatments. So we tested 4 different type of DRA. Number 7 is experimental DRA, so I can tell you what it is. And also number 8 was T40 spraying water, but flying across the rows. All the other treatments were flying along the crop rows. Now treatment number 8 flew across the rows at a 90-degree angle, perpendicular to the rows. And number 9 was the airplane treatment at 2 GPA. I'll show you the info a little bit later. All right, let's take a quick look at the weather data. Like I mentioned before, we got more wind this year. And that weather station we use, Watchdog doesn't lie. It recorded all the wind speed, wind direction, temperature, humidity at all the time when we spray. All right. So you can see the variation of the wind speed across the days that we spray those trials. Yeah, I mean, I don't like to spray 12 or 15 mile per hour wind, but that's just the type of wind that we got at that time of the year. So, this year I was like, well, let's just spray, because I know the commercial drone operator is gonna spray anyway. They're gonna spray anyway. So we just sprayed with whatever wind we got, hoping to avoid some really bad gust. But still, way more wind compared to last year. And also because the size of the trial, we cannot complete all the treatment in the same day. So if you look at a date of the application using different the application date of different treatment, it usually across a 3 to 4 day period, but I doubt that the date down here is correct. I think this was done in the same day, June the 23rd. I need to check with my student on that. All right, the second application was all done in 1 to 2 day time frame. I think it's a 2 day, July the 19th to the 20th. So first application, these are all first application. This was done in mid to late June. Second application was mid-July. And also between the first and second application, we had a pretty bad heat, and also the drought start to get on us. So we're seeing less and less rain. That's when the high heat condition in Texas was really bad. And it started to crawl this way. Going to the southeast. So it was hot and dry. Canopy, the corn canopy at both sides did change a little bit, although they were under irrigation. But as you can imagine, after 3 weeks, from the first application, the canopy start to die down a little bit. We start to see, yellow leaf, and the edge of the leaf start to turn yellow, because they're older corn. And my student told me putting the milo cards and the water sensitive paper on the corn leaves become more difficult because that canopy just starting to get desiccated. There's not much water in there. So the canopy structure changed a little bit. We do want to sample more planes, and we just had our hands full with the first application. That's why we have to wait for a little bit, finish some other projects before we can call 2 more planes again to run a comparison study. But still, I think data has a value, because the corn canopy, and I should say plant canopy or crop canopy in general plays a big factor of how your quality the job can be, and we need to spend a lot more time to understand the crop canopy. So some of you may wonder why you spray with T20P this time. The reason was simple, because we had a forced landing with T40. Arm was broken, propeller was broken, antenna was broken, a bunch of things had to be replaced. So T40 was in the shop waiting to be repaired. We just have to spray with T20P, which has the exact same rotary nozzle, the rotary disc, and very similar design as the T40. So this one was actually sprayed with T20P. And then we had two airplanes to compare the results to. All right, looking at the weather data when we sprayed on those 2 days, still at the same two fields where we did a first application. Wind was a little bit lower, but not by a lot. Still between 8 to 10 miles per hour. I say this is a lot of wind. I don't feel too comfortable with the wind, but it is what it is. We have to get a project done. Wind direction was fairly consistent during the application. All right. And then many of y'all want to see the airplane information. I know some of the audience may have crop dusting experience or might be a crop duster, a commercial crop duster and spray crop now, just interested in spray drone, or you guys know a lot more about airplane and spraying system on the airplane than I do, because I don't fly airplane to spray my trials. So these are all the information I got from crop dusters. All three planes are commercial spraying planes, so they all claim they go through airplane clinic every year. They go through strain testing during the off season. They calibrate their planes, so everything is accurate. All right. So I take their words, let's just say their flow rate is accurate. They calibrate the instrument and everything's supposed to work as it should. Something to notice is for the second application, these two planes flew a little faster, 170, 160 miles versus 130, 140 miles in the first application. Swath width is also a little wider than the first airplane. All right, altitude was a little lower for the first plane compared to the other two planes. This first plane we used was also the same plane we used in 2022 study, because this plane did a good job. We called a crop duster and say, hey, you want to keep spraying for us? He said, you sure, why not? And then with that being said, let's continue. So we sampled 3 airplanes in total. Each plane sprayed both sides, Columbia and Blakely. And then the application was made on tassel corn after pollination, so these are full-size corn. We didn't spray the little babies. Fluorescence dye and water-sensitive paper were used for data collection. And also data collection was mostly done on the ear leaf. For vertical sampling, we used the second leaf above the ear leaf and also the second leaf below the ear leaf along with the ear leaves. So we have 3 leaves in total when we do the vertical sampling. So you're going to see the data in a minute. Okay, for Columbia side, this is how the corn looks. It is thick. All right, so walking in this cornfield wasn't that easy. This is a high yielding cornfield under irrigation. This was the picture I took at the first application back in June. So corn was very juicy back then, so with full canopy. And yeah, let's look at a video. That's basically how thick it gets. All right, for the data collection, this is the metal card, the plastic metal card we put on top of the collection leaves. And also we put the water sensitive paper on top of the metal cards, so we can collect the droplet size information, the percentage of coverage on the water sensitive paper, and also we know how much dye landed on the metal cards. That's basically the methodology is. And then this is the Blakely, Georgia site. My PhD student, Livia, was there leading the crew. So she did a lot of hard work over there at both sides, along with my the other grad student, Tiago. So a lot of time is Livia leading crew at one side, Tiago leads the crew at the other side. Both of them spend a tremendous amount of time and effort to get a study done. We can't really do this without their dedication, along with all the student interns and student workers, because this type of application study takes a lot of manpower. Last year, at one site, we had 17 people running at the same time, in one field to get it done. You can see the dye droplet on the milo cards and also the coverage on the water sensor card as well. I don't even know what treatment this came from, but I want to say this one was sprayed by drone. This one, because I took the picture, I know this one was sprayed by the airplane.
Sun went down and the jungle fire was burned.
Hey, Mark, was that you?
It was, sorry.
Okay. All right. So you can see the droplet size were different. The airplane has smaller droplet size versus the drone treatment had a bigger droplet size. Does that translate into any difference in the study? That's something we'll find out. All right. Now is the most interesting thing that you guys are waiting for or have been waiting for a while. How does drone application compare to airplane? From our study, as you can see, the downdraft is different. Airplane going through on top of the corn, the tassel doesn't even move that much, versus T30 spraying on top of the corn. You can clearly see how it pushes the corn aside, the canopy aside. So does that make a difference? That's what we're trying to figure out. I didn't shoot a video of T40. I was hoping to, but just schedule didn't work. That was the last year's video. Hmm. All right. So most important thing is the dye concentration, because we mix the spray dye just like mixing chemical, so we know how much dye we sprayed in terms of the weight, like the active ingredient weight per acre, So we consider dye concentrations to be the most important standard, in our evaluation. Airplane, this is from the first application. This is the same plane I used in 2022. So this is a good plane. All right. Basically, dye concentration on year leaf showed no difference between T30, T40, and airplane in Columbia and also in Blakely. All right. So statistically, they were all the same. We actually saw airplane created the highest numerical number of dye concentration on the year leaf, but statistically they were similar, they were equivalent. And then let's look at the vertical dye samples. Remember the vertical canopy penetration that I was talking about? So now we have year leaf, the high leaf, the low leaf. Excuse me. The high leaf means the second leaf above the year leaf. The low leaf means the second leaf below the year leaf. And the year leaf is year leaf. All right. So you can see the dye concentration on those three leaves collected by the milo cards. Higher leaf tend to get more dye compared to the year leaf and the lower leaf, which totally makes sense because that's the first leaf on top of the canopy. It should retain most of the dye or the chemicals. But again, that's not a goal. We don't want to land all the chemicals or fungicide on the high leaf. We want it to go to the low leaf, go below the canopy. All right, so that's a distribution there. And also another interesting finding is we saw higher concentration on the leaves, at Blakely. 1 second. We saw more dye concentration at Blakely versus Columbia. This is true for the airplane. Let me go back. And this seems to be true for the drones as well. Higher concentration at Blakely versus Columbia. So I asked my grad student why, and they think the canopy, the corn canopy at Columbia side was thicker. It was more difficult to walk in the corn canopy at Columbia versus Blakely. So that was their explanation, And that seems to make sense too. So this is a point I actually want to make. not all jobs are equal. Not all fields are equal. Not all crops in all fields are equal. So you will have some variation between the fields. Depends on how tall the crop is, the variety, whether this is dryland versus irrigation. You know, if this is a pioneer versus decab or whatever, pioneer corn tends to get tall and thick. That's going to be difficult to penetrate a canopy, you know. So think about the variations, you know, and that determines the job quality as well. So all right, more interesting stuff. This comes from the second application. Remember, in the second application, I used T20P. So this is not even T40. This is a T20P. So T20P is lighter, so it didn't have that much of propeller downdraft versus T40. So maybe that's a factor there as well. But looking at the results, again, dye concentration, spray dye concentration on ear leaf. Now, some of you guys may start to get excited. All right, look at airplane 1 and airplane 2. We start to see lower dye concentration on the ear leaves versus T20P with no DRA, that's just straight water, and the T20P with DRA. So two things I want to point out here. You know, I have time today, so I don't try to rush through the slides as fast as I normally would. So two things to keep in mind here. Again, this is what data suggests, you know, and it's not final conclusion, just basically what data shows. Not a lot of difference between DRA and without DRA, because this is second application. You know, the corn canopy has shrank and died down a little bit, you know, desiccated a little bit. I think that opens up the gap, you know. So even without DRA, probably the droplets can get into the canopy a little easier. Now that's my explanation why there's no difference between DRA and no DRA. And also, we saw more dye concentration on the ear leaf for the drone versus the airplane. So how did that happen? I don't really have a good answer for it or assumptions. I can say the planes are different. You know, remember these two planes flew a little faster, spray a little wider, and spray a little higher. Maybe that's the reason, you know, a little bit more aerial drift loss. Remember, you know, we also had a wind, so maybe drift was part of the reason why we saw lower concentration for the airplanes. I mean, I don't want to say these two airplanes are not well calibrated, but that could be a problem. You know, if your flow meter is not calibrated, you think you're spraying 2 GPA, but you're spraying, you know, 1.7 or 1.5 GPA. Sure, that could play a role there, you know, so your flow rate has to be calibrated and accurate during our application. That could be another reason, but I don't want to speculate. It could be caused by airplane or something else, you know, but what we see is what we see, you know, you can't change the data. All right, showing you the percentage of coverage data from the water sensor paper. Again, no statistically different between the DRA and the no DRA, that's straight water treatment. All right, so no effect of DRA here either. All right. And then significantly higher deposition or percentage coverage on the water sensor paper between the drone versus the airplane. You see the letter was ABA and this is B. So this one is statistically same as that one, but this one's statistically lower than both of these. All right. Over here is easier algebraically. Both airplane produce lower percentage of coverage on the water sensor card, water sensor paper on ear leaf compared to the spray drones with or without the RA. So these are the deposition, you know, percentage coverage data from the water sensor paper on ear leaves. What about dye variation on ear leaf? Similar. Still, we're in this magical range, 60 to 80 or 90%, you know. Over here, yeah, probably still, yeah, 60 to 90%. This one is a little higher. I don't know what happened. Maybe this could be because of the wind, you know. Wind will create wider arrow bars and more variation, but still we're looking at a similar range of a CV between 60 to 90% on our sample. This was consistent to 2022's data. All right, what about VMD? I already showed you all the picture, you know, of the drone sprayed card versus airplane spray card. Visually inspection, drone spray card has bigger droplets. So after scan those cars, yes, the observation was confirmed. Drone sprayed treatment had a bigger VMD, generally speaking, than the airplane. We don't have enough time to run the stats. We should have finished the statistical analysis and mean separation here. This is why you don't see the letter here. It's just because we're so busy. We still haven't finished data processing here. So at the end, we're gonna put letters on here so you can read the mean separation by yourself. But we set the droplet size on the controller to be around 300 micron. That's what we set on the controller. After you mix chemical, typically you make a little thicker. In this case, we saw bigger droplets than 300 micron. But there could be variation there as well. So you shoot for 300 micron, you may get a little bigger actual droplets. So that's what we saw in the data. And also looking at the vertical sample collections or the vertical penetrations, we still have the high leaf, 2 leaves above the second leaf above the ear leaf. This one is ear leaf, and this one is the second leaf below the ear leaf. That's what we mean by vertical collection. You can see the distribution or the concentration distribution on those leaves. So the interesting thing is on this canopy, which is a little bit dried down canopy, we had similar dye concentration across the three leaves, and for these 2 cases, ear leaf actually got most of the spray dye, numerically. This is not going to be statistically different. But the difference is the drone versus airplane. All right, so how do you read this? The way you read this is if the A has the same color as this A, which means this one got a orange A, this is orange A, this is orange A, and that's orange A. That means these 4 orange bars are statistically the same. All right, looking at this blue, kind of weird bluish color bars, if this one got A, this one got A and B, that means these 2 are statistically the same. But those 2 bars are statistically higher than this one because this one got C. And this one and that one are statistically the same because this one got C as well. But the bar over here with A is statistically higher than B and C. All right. So that's how you read it. But if you look at both sides, generally speaking, we saw more dye on those 3 leaves when we spray with T20P, particularly the lower leaf sprayed by the airplane, This one got a perfect separation. See, bound, basically high, middle, low, high, middle, low, high, middle, low. All right. This trend is not that obvious with spray drone. I mean, it's somewhat true. This one is like high, middle, low, but not here, not here, and not here. All right. I think it was caused by the propeller downdraft. Mark may have something to add later. With airplane, you don't get a lot of wind blowing into the canopy, so you tend to have this nice high, medium, low separation a little bit more pronounced. For drones, it makes a mess with that propeller downdraft, so it's kind of all over the place. All right, that concludes the drone versus airplane comparison. I know I cover a lot of data. Some of you may already got confused, I hope you're still with me. I'm getting close to the end of the presentation here. I know I'm gonna take a little while to finish everything. So now we're gonna look into the spray drone type, GPA, flight direction, and DRA evaluation. All right. Again, we're looking at percentage coverage on the water sensor paper on ear leaves. This data set came from the first application. Looking at both sides, all right, we typically use T30, T40. These 2 bars were sprayed, or these 2 treatments were sprayed with just water. And also look at the airplane as a reference treatment. This one was just 2 GPA airplane with only water. All right. So if you look at the percentage coverage, of these two bars, T30, and the T40 with only water, and also T40 flying east and west instead of north and south along the roads, and also the airplane bar. These two bars and these two bars remain the same. It seems that trend remained the same compared to the T30 and T40 and the T40 east and west or west and east and airplane. So these four bars remain pretty consistent across the two fields. The DRA ones, the one with DRA and also the T40 at 3 GPA, we saw a bunch of variations, particularly T30, T40, 3 GPA at both locations. This one got about 1% coverage. This one was way higher, it was a lot higher. And also the Intact Pro, the RA didn't do too well at Columbia, but it did really well at Blakely. All right, it did really well here. Ultra Lock, which is the Winfield best DRA with methylated acetyl, a bunch of stuff in it. I think it's an expensive one because Winfield gave me a bunch of samples. They're pretty supportive for research. I got a few cases. So I said, okay, I'll throw this one in and see how it does. And I also AccuDrop is Winfield's DRA as well. You see, these two perform fairly consistent across both fields, particularly if you compare these two bars to the reference treatment, like a background treatment. All right, like this treatment compared to here. Yeah, it just increase the deposition here on the ear leaf. Again, I apologize, we don't have enough time to run the stats. I hope I have the letters here so I can tell you whether this is real or not based on the statistics, but we haven't done it yet, so we can only eyeball the bar and arrow bars, and tell the story here.
Hey, Steve, I want to
Yeah.
bump in there real quick. This is percent coverage, so it's the pixels that were actually colored on the water sensitive paper. That doesn't necessarily, those DRAs could very easily be spreading, the spread factors could change quite a bit. So increasing the percent coverage without knowing other data doesn't necessarily mean you got more deposition on the plant. It means you just wetted a larger area.
Yes. That is true, and that's actually one point I want to make next. I don't necessarily always believe percentage coverage data. That's why I say water sensitive paper is a good tool to have. But look at the stuff here. I believe the fluorescence dye more than the water sensitive paper. I said this earlier in the training, and this is why.
Well, they both tell different parts of the story. None of these things tell the whole story.
Yeah, none of this tells whole story. True. Well, I'll talk about this point at the end, because the only thing tell the whole story, the true story, is the efficacy. But I hate to tell you this, Mark. Efficacy wise, we spray fungicide on all these fields at all these sites this year. We may not have any difference because we don't have any disease there. So that's the ultimate truths, that I'm trying to dig into, but they may not be available this year. I hate to say that's 2 years in a row. But again, water sensitive paper and dye, they don't always agree with each other, but I like dye better because dye simulates the real chemical better. At least I know the quantity on the leaves. It's not a true representative of the actual spray droplets because the viscosity could be different, but still, as a relative comparison, you can see in Columbia, Alabama, we don't have a lot of differences here among the treatment. Basically, it's not significant among all treatments. So all treatments perform equal. But at Blakely, T43 GPA and Intact Pro had a significant higher dye concentration, and also Ultra Lock did pretty well. All right, so that's some of the things we noticed from the dye data here. If you look at the first application, I'll go back to June. We had a T40. This was from the first application as well. And also I pick out this 3 treatment. T40 water only, T40 3 GPA. This was 2 GPA versus 3 GPA, and also T40 flying east and west. Statistically, no difference. except for this one. Actually, 3 GPA did it better than T40, Flying East and West, and 2 GPA. But among those 2 GPA treatments, whether you fly along the road or cross roads, didn't matter. At the Blakely side, 3 GPA did significantly better than the 2 GPA treatments. Again, for the 2 GPA flying along the road and across the road, no difference here. All right, I think in the next presentation, in Jason's presentation, he has data to show that 2 versus 5 GPA, and the 5 GPA beat 2 GPA by a pretty wide margin. But here you can also tell flying direction didn't matter that much. Dye concentration on the year leaves typically is between 60 to 90%. Over here, we even saw a little higher, over 100%. This is a little unusual, probably caused by the wind, but typically between 60 to 90 is normal. I think this year's data show a little bit more variation because the lowest bar was around 70%, and actually the highest one was over 100. Remember, last year was between 60 to 80. My assumption was wind, because we sprayed with more wind this year than last year, so we saw more variation. Remember last year when I had a ground rig to compare, when I had a 1 to 2 mile per hour wind, I had a CV as low as a 40 to 50. I didn't see that this year with 8 to 14 mile per hour wind. For VMD, it's kind of all over the place. With the DRA, we saw a little bit bigger VMD. That's somewhat expected. I don't know what happened here. T40 water only, lots of difference between the two sides. There's a big change of VMD here and there. Except for a few DRA treatment increased the VMD in general. There's not a whole lot of things to see. Airplane did produce a fairly small droplet. This is a fine droplet. It's just a little bit over 200. All right. So a quick summary for the 2023 study. Still a lot of information out there. No statistical or noticeable difference between the T30 and T40 for the guys spraying with hydraulic nozzle drone versus the rotary disc drone. You can expect fairly similar results as long as you set the machine correctly. 3 GPA generally increased coverage and dye concentration compared to the 2, although it's, at the one side it showed real good difference, and the other side only show a trend of increase. Flying across the road did not improve the results or provide any benefit versus fly along the roads. So they were basically the same. So that means when you plan your mission, if the most economical way for you is to fly across the road or fly at an angle, I don't think it will make that much a difference compared to fly along the roads. But you can make a call, for that field after you see it. DRA generally increase the dye concentration and the coverage, although this is not always true as a general trend. It seems that ultra-log and AccuDrop are more consistent, but the issue with ultra-log is, and also interlock and master log, those are oil-based DRAs, so expect they may give you a little headache when you mix them with your foliar. So a tank mixing compatibility test, a jar test is needed if you spray a foliar feed that you never used before. We saw little improvement on spray uniformity with DRA this year. It's not a lot of difference. Let's see. Okay, percentage of coverage and dye concentration generally agree with each other, but not always. Like Mark said, they tell a different story. But most of the time they agree with each other, but I've seen a couple of times that they don't. Dye concentration was higher at the Blakely side than Columbia side, possibly due to the canopy differences. I think we got a little thicker corn at Columbia than Blakely this year. Drone treatments generally had a bigger VMD than airplane. I set 300 micron on the remote controller. What I got was a little bigger than 300, as you saw the data. In the second application, DRA didn't increase dye concentration and coverage versus water alone. That's not a huge surprise considering the canopy has changed a little bit over that 3 weeks period because the high heat and high temperature and low rainfall. T20P produced better results compared to the 2 airplane tested under windy condition. Reason why, I don't know. We have to keep working on it. I don't want to make it a conclusion yet because we only sample 3 plane. That's a very small sample size. We need to sample more plane to get a better representative better representation of each equipment. Again, like I said before, spray drone using the 300 micron setting on remote controller actually produce bigger droplet size than the airplane nozzle on the ear leaf. So if you want to shoot for smaller droplet size, you can set it to 250 on the controller. You probably will get 280 to 300, something like that. All right, I already mentioned this last point here. So don't want to make it sound real conclusive here because there could be multiple reasons or factors contributed to the difference between the drone and the airplane. As of this point, we still don't know enough, because the canopy differences can play even bigger role than the equipment. All right, right now I'm moving on to my last page, and I think we need to use a break according to the agenda. So I got about 3 minutes left. At this point, based on all the data I collected in the last 2 years at multiple sites, I tend to believe drone can deliver corn fungicide in a similar fashion compared to the airplane, and even compared to the ground rigs, even comparable to the ground rigs. It's too early to make a final conclusion about drone versus airplane, which one's better, especially when you run your drone at the maximum efficiency. We know it's going to be flying fast, and the job quality will be a little lower with the high efficiency setting. So still more work need to be done, more planes need to be sampled. Hopefully we can make this a regional, more than regional, make it a national, or it could be an international project, if I have more collaborators to participate. I think tank mixing DRA is generally a good practice. You have seen the data that I saw. Although it's difficult to identify or tell you which DRA is absolutely the best, I'm not sure if that can ever be possible, because you run 10 different evaluations, 10 different trials. You can get a top 3 candidate, but that's about it. Just like on-farm variety test, which soybean, which corn, which cotton variety is the best across all over the country. You're not going to be able to find one. Different regions have different variety that do well. I think it's kind of similar for DRA. There are lots of DRAs out there, so evaluate all of them. That's literally impossible, So to be able to identify the best candidate, that I just don't know if that can ever happen. And also the incompatibility of DRA in your tank mix, particularly when you add a thick foliar nutrients in the tank, that warrants further investigation in future. Flying direction had a minimal effect on spray quality, which kind of provides the flexibility in route planning. You don't always have to fly along the corn rows for whatever reason. If you want to fly across rows, then that'd be fine too. More GPA is generally a good thing. I only had 2 locations this year, and one didn't produce significant difference between 2 and 3 GPA, so I don't want to make it sound real conclusive. We need to keep testing GPA effect on deposition, and the coverage in the future. But I think in the next presentation, between 2 to 5 GPA, you can see the similar trend and similar results. More water is usually a good thing. Make the drone fly at a consistent height is difficult, particularly on rolling hills. I already learned that lesson. The new firmware update is not very helpful. And also T40 fly faster. So generally it puts more stress on the drone to maintain a constant height when you fly faster, DJI or whoever, other manufacturers, if someone can make a drone that flies a 30 mile, 40 mile per hour, but maintain a really good height above the ground on rolling hills. That would be wonderful. Again, not sure if that can happen or not in the near future. Hopefully it will. Still avoid wind as much as possible. We saw the CV, the coefficient variation or the spray uniformity decrease in this year's trial versus last year's trial because I had a lot more wind compared to last year. Last year I can reach similar coverage, not coverage, similar uniformity, even comparable to the ground rig. This year it was way higher than that. All right, that's give credit to the wind. When you spray with a lot of wind, you're going to create a lot of variation, in the field. There will be hot spot, cold spot, hot spot, cold spot of the pesticide coverage. And also I throw out an oddball number here, 2.34 GPA. You may wonder, what the heck is this? What does that mean? That means if you fly a 30 feet swath with T40, I feel comfortable with 30 feet. Anything above that 32, 33 feet, that's going to be a stretch, particularly if it's windy, you may or may not get that wide swath, so you may have to reduce the swath width a little bit. If you fly 30 feet swath and use a top speed, 32.8 feet per second, you max out your flow rate to be 3.17 GPM, gallon per minute. If you run a calculation, I did this right before the training, you will get a 2.34 GPA. So that means you can run 2.34 GPA without slowing the drone down because you just max out your flow rate. Does that mean even though somebody pay you 2 GPA, you can actually spray a little bit more and use that as a selling point? Because you're spraying more gallon per minute, you finish a tank load a little quicker. Although you have more volume, overall, you have more volume to spray per acre, but you spray it quicker as well. Maybe at the end of the day, it doesn't really slow you down much, but you do increase your job quality and deposition here, because you're putting out additional 0.34 GPA versus 2. So, anything helps. So is that going to be a thing for people to use? I think we can use a little bit more study in future to quantify this, especially after we get swath gobbler. Now, we can use it to test deposition on flat ground fairly fast using the new equipment. All right, I want to bring out 2 more slides to show you our southern crop, cotton here, because I want to make a point. For cotton, you do have to defoliate a crop. Because if you don't defoliate, you can't pick it. I mean, you still can, but you're gonna get lots of leaves along with your cotton lint. And no cotton gene wants to buy your cotton anymore because it's super difficult to separate out the dry leaves from the white fiber. They just want the lint. They just want the fiber, not the leaves. This is why we have to defoliate the cotton. And also, in the cotton defoliation, we mix bowl opener with the defoliants to open up some of the new young bowls on top of the plants, hoping to get a little bit more yield, because lower bowl mature first, younger bowl on top of the plant mature later, So last fall, we ran a study to evaluate if DRA, drift reducing agent, can increase defoliant efficacy and also increase the canopy penetration. So we use petri dishes last year because we can put them underneath the canopy. At the cotton defoliation, you got some leaf on the cotton, but the canopy is half beat down because it's kind of dying down anyway. So it's more open than the cotton, than the corn canopy for fungicide for sure. So just want to bring out the data. We got airplane versus drone with 2 DRAs, Now you're looking at the deposition data using the fluorescence dye again. This is a farm plane, so the flow rate is not accurate. So it didn't really put out 2 GPA, put out lower than 2 GPA. The farmer didn't even know until we tested. So I want to point out this first. Drones did spray 2 GPA, but airplane didn't. My guess is somewhere around 1.5 GPA, or could be even lower than that. So this is why on the petri dishes, we saw lower concentration of the dye from the airplane versus the drone. The T30 blew more dye into the canopy. Again, with those type of semi-open canopy, DRA didn't, play a big difference here versus water only. All right, that's the point I'm trying to make. The canopy characteristic, the canopy thickness, that plays a big difference in terms of the canopy penetration of your droplets. So DRA may not always work, depends on the canopy characteristic. And also, the question is, Mark asked, what's the ultimate goal? What's the ultimate standard? The ultimate standard is the efficacy, So this is actually serves as a great example. Some people may also wonder the same thing. Hey, you showed in your second application of corn fungicide, those two airplanes produce lower bar, which means lower concentration on the ear leaf. Does that necessarily translate into a difference you can see at the end of season, yield loss, more disease, or whatever? The answer is it's all hard to say. But in this case, I'm showing you with cotton defoliation, and we clearly know this plane doesn't spray 2 GPA. The pilot thinks he sprayed 2 GPA. He might be only spray 1.5. All right, so we know it spray lower concentration. Does that translate into a difference in terms of percentage defoliation or visual rating of defoliation? The answer is no. All right, that much of dye difference was not enough to make a difference in the golden standard, which is chemical efficacy. You see all these 3 bars are the same with DRA. With DRA, we seem to get a little bit better defoliation than the water alone, but this was not significant, only a trend. But this was airplane without DRA. This was drone without DRA, spraying the same defoliant, same rate, and everything was the same. These are statistically the same, although the dye concentration is significantly lower for the airplane versus the drone. So there's no right or wrong answer. It just depends on which angle, which perspective you use to analyze the problem. So this is one way to look at the problem. There might be some differences with that fluorescence dye concentration on the leaves, but at the end of the day, it may or may not make a difference. So some people ask, are you gonna keep doing this type of stuff next year? Yeah. I told my grad student, this type of corn application project probably will continue. So next year, we still want to focus on high efficiency versus high quality comparisons. And then drone versus airplane comparison will continue as well. We want to sample more airplanes. More DRA evaluation, this will continue, maybe using different type of DRA, maybe using same DRA, a little bit different fashion. The last thing is pretty cool because I will get an aerial drift collector from Mark, so we can run this study next year. This is a new thing. So we not only want to quantify the spray dye deposition into the canopy, we also have a new way to measure aerial loss and use this aerial drift collector to catch the dye flew away from the application area. So I can calculate a ratio between the deposition and the aerial loss and see if this ratio is or can be, or if this ratio can be affected by the DRA as well. So that's going to be some of the things we want to focus on next year, just adding more tweak and more perspective to analyze this problem. So this year we learned something new as well. We were able to make a DRA significantly increase the dye concentration on the ear leaf, and we learned more about canopy structure or canopy differences, and how that affect our results. So canopy is a more complicated thing than I originally expected. So still, learning something new every day. All right, at the end, I want to appreciate my grad students for their hard work one more time. And without them and my student worker and the student interns, none of these data would ever exist. I basically will be a useless old fat guy telling jokes in front of growers and operators. So You know, they deserve the credit for sure. And I also want to appreciate my funding agency, Alabama Farmer Federation, Alabama Wheat and Feed Grain Commission for their support. I saw one question. What the drift reduction tag you have in the tank for droplet uniformity? Oh, you can go back to recording. I have the names listed on the treatment page. You can look into those information yourself and search the label online. I mean, Ultralock is fairly famous and most of people know it. You know, the other two may be a little bit less famous, you know, that I used.
Hey, Steve, can I chip
Yeah.
in? So a couple of thoughts here too, that we've been talking about the coverage pretty, exclusively, whether or not it's quantitative or qualitative. One of the things we've got to recognize in this too, that the cotton defoliant is systemic, and Miravis, Delaro, the other corn fungicides that are used also have locally systemic activity, because the coverages that we're talking about here are really small. You know, if you were using a contact material, getting 1.5% coverage may not be a successful spray. But
Mark,
anyway,
cotton defoliants are contacts.
are they contact? Okay.
Oh yeah, they are contacts.
Okay, they're not using a systemic killer. Okay, that's it.
No, sir, they are
Okay.
contacts. If you miss a
Interesting.
spot, you will see it.
You'll see it?
well on
Okay.
UVI. Yes.
It's my northern bias.
Yeah. So this is why I brought out the case, you know, of cotton defoliants. Even though we saw a significant reduction in the dye concentration on the petri dishes, I wish I put a water sensor paper in another petri dish so I have the percentage coverage. And at the end of the day, it didn't make that much a difference in efficacy. You know, and we also know the airplane is not accurate. It's putting less product than the drone. You know, still.
Well, and to be fair, getting that kind of coverage on petri dishes at the bottom, and that's the toughest place to cover in the canopy. That's actually not horrible.
No, it's
I mean,
not horrible.
With ground sprayers, to see coverages like that at the bottom on the ground would not be those would actually be considered pretty decent for ground coverage.
If you have interest, I'll show you one more thing. I'm sorry, I'm off the topic, but since Mark brought up cotton defoliation, this is a presentation we made at Beltwide Cotton Conference. This is hosted by National Cotton Council, the biggest cotton conference in the U.S. Because you mentioned the versus ground rig, I didn't pull up the data. Let me share my screen one more time. Just real quick, and then we'll move on to a short break. We also sprayed another field. You can see drone treatments, 15 feet height, 25 feet swaths, 15 feet high, 20 feet swaths, 10 feet high, 20 feet swaths, T30, versus ground sprayer. These are just normal John Deere sprayer, not air assisted, not electrostatic, not a fancy one. Just normal ground sprayer, Mark. 2 GPA, same product, same defoliant for AI per acre. You know, only difference is GPA and the delivery methods. 2 GPA versus John Deere ground rig 10 GPA versus same sprayer 5 GPA, percentage of defoliation rating on the ground. So 10 GPA created similar results as the drone, you know, 2 GPA. But if you look at 5 GPA here, this drop is significantly different. So typically we tell grower, if you want to defoliate your cotton correctly, you got to use plenty of water. And I'm just going against that rule. I'm going lower and lower. 10 GPA might be as much corner as you can cut. When you go with 5 GPA, you're gonna pay back because you're gonna have to come back, defoliate again. That costs you money and time, you know.
Well, and when you're spraying with a boom sprayer, the only way you can transfer the chemicals with water, we've got that beautiful downwash with the drones, which we're using air instead of water for the transfer media.
Exactly. So, that's what we have here. We have the wind, we have the propeller downdraft as a carrier for the pesticide. Yeah.
Yeah.
So
Yeah, and looking at the one you got there, the one that's closest to the canopy and the narrowest swath, you really pounded that canopy.
Mhm.
That's, yeah.
Yeah, and I'll show you this as well. Airplane, you saw this. This is airplane 3 GPA versus T30 2 GPA. Again, I got propeller downdraft. I can blow this stuff in the canopy if I want to.
Mm-hmm.
This is cotton before defoliation. This is how it looks. You still got leaves, but look at, you can see the ground clearly. You can see the ground. This is why I say the DRA didn't play that much a factor here, because it's already half open, you know. It's a different canopy. That's why I say I'm learning something new every day. Canopy thickness, canopy structure, how the leaf oriented, all of these, and the texture of the leaf, all these things matter, you know. All right, I may have talked too much again. Let's go. When defoliating, did you use a 3-way? Yeah, this was a probably 4-way, I would say. It's a bunch of different products. I'm sorry, Caleb, I can't tell you exactly what I used for defoliants, but it was a 3 or 4-way mix with a bowl opener. Bowl opener was one of it. Erdo asked a question, high efficiency versus high quality. Please explain this a little bit. Well, high efficiency means I stretch the drone to the limit. I can cover as many ground as possible, allowed by the machine, basically. So that's what I mean by high efficiency. High quality is I reduce the speed, I reduce the swath a little bit. I put out 3 GPA versus 2. So I frame it as a high quality. You can go back to the treatment page to look into the detail setting. It's in the treatment page. Or something like ET. I'm not sure if we use ET or not. I don't think we used ET last year. Some people use ET, but ET is more common as a desiccant. I don't know, maybe. I have to go back to my book and see what we exactly applied with that with the cotton defoliants. Mark, any other questions?
We'll probably get into it to the other thing too, but
Uh-huh.
going back to I love the 2.34 GPA thing, because and I mentioned this in your prior thing too, that a lot of times GPA winds up being a surrogate for speed. If you're going 3 GPA, you've got to slow down, so you're really pounding the canopy more as well.
Mhm.
And since we don't usually report, well, you reported speed, which is good, but oftentimes it's not. People just fly the drones as fast as they can. 3 GPA, you should looking at the canopy, you should find the same amount of dye per canopy somewhere.
Um,
Yeah, as the water rate gets higher, but you wind up, just pushing it down so much harder.
mhm.
Even flying just a few feet per second slower concentrates a lot more air energy in there.
Yeah. Yeah, that 2.37 GPA, whatever I came up with,
Yeah.
that's a number that I don't have to slow down the drone or reduce the efficiency, and then I can put out a little bit more water per acre,
Yeah,
hoping to get a little better coverage and a better rooster tail. The vortex around the drone kind of help me even out the droplets a little better, because I'm putting, just about 15% more, so no, almost 20% more. Hoping that 20% more water volume can make a difference. That's my assumption. I don't know if it works or
yeah.
not. Yeah, I'll try it on herbicide first, because herbicide is the one that if it works, it's gonna show up real quickly.
Well, you've watched a million swaths at this, or a million passes at this point. Do you think are there scenarios where you can go too slow?
Are you able to go too slow?
Where you're just pounding it too hard and not and you're I mean, not only is it costing you more because you're going slow, but your swath starts to degrade because you're pushing it in too hard. Are you seeing any scenarios that way?
I guess that kind of depends on row crop or specialty crop. On row crops, yeah, you can definitely go too slow, and that creates a streaking problem. You know, you concentrate too much chemicals underneath the drone, not enough overlap. I mean, that's gonna be a problem for large acreage row crop. For specialty crops, particularly like a tree crop, you know, really thick canopy, flying, you know, 5-6 feet per second and blow as much volume as you can into the canopy actually work out pretty good for me.
Yeah.
You know, that's why I say it all depends on the canopy and your operational goal. If you want to cover more acreage, that you got one way to do it, but if you wanted that air flow, you know, the airflow as much as you can, then you gotta fly real slow. Yeah. All right, I share my screen one more time because somebody asked again what type of chemical you use. Here is the official answer. You can look at the thing I have here. You know, it's actually a three-way mix. It's actually a three-way mix, and we didn't use ET. I recall we didn't use ET because I don't like particularly like that chemical much in defoliation. All right.
One other thing while we're a lot of those DRAs are multiple multiple benefit packages where they've got, it's not just a DRA, they got a spreader, they've got they've got different how much do you think the adjuvant package over and above the DRA has to do with some of those higher coverage numbers?
Not a lot. I know some of the DRA package has defoamer, which is still good to have because foaming is a big problem. If somebody built a really nice package of a good DRA with a good defoaming agent, I'll buy it. I say it's worth the money because that foam can literally decrease your efficiency by over 20% because you know that T40 tank, if you don't run defoamer, you can only fill it up to 8, maybe 8.5 gallon, and then the top layer is just all foam. You know, if you don't fill up the tank full, basically you're losing efficiency. You know, for nothing because you don't fill up the tank full. Some of the DRA package has adjuvants built in it, ammonium sulfate, crop hull, NIS, and whatever. That part I'm not too sure. You know, that's kind of getting to the iffy stuff. You know. Ammonium sulfate, maybe I'll buy it, but the other things, it just kind of depends. Every situation is different. If you see an issue late season when running a high rate of ethaphone, say 42 ounces, that's a question for our cotton agronomist. You know, I don't answer that type of question to that level. You know, but spraying wise, I'm not foreseeing too much of an issue, but efficacy wise, I don't know. You know, you have to ask a cotton agronomist for that type of a question related to one single chemical. All right, should we take a short break or should we start to play Jason's video? Because looks like we're behind the schedule again successfully.
Yeah, we lost a few folks.
Yeah, we lost a few folks, I know. All right.
I'd say go for it.
I'll just go for it, yeah. Most of the folks are probably pretty tired today, you know, most of them didn't show up. I'm sure they just want to watch a recording. All right, let me open up Jason's video so I can share it.
Hello, everyone, and thanks, Steve, for having me here to deliver this presentation. Sorry I can't do this live, but with any luck, I'm in a kayak somewhere in Northern Ontario. But don't worry about it. My colleague, Mark Ledeborough, is going to be online to answer your very, very difficult questions. Please make them hard for him. He needs a challenge. We did a study on coverage and drift in field corn last year from an RPAS system. And I'd like to talk to you about it, but I'd like to start with the acknowledgements. First, our funding partner and our in-kind partners. That was Adam Pfeffer and volunteers of Bayer Crop Science, Adrian Rivard, our long-suffering drone operator with Drone Spray Canada, our grower cooperators, Nick Hoffsumner, Brad Fife, and Dan Petker, and my colleague Amy Shee, who without her, I could never do the stats. So why did we care to explore drones in corn? Well, there's increasing demand for corn spraying. There's concern about insects and disease. You're all aware of gibberella ear rot and tar spot, just making its way into Ontario right now. We know that timing and product choice, as well as variety choice, can help with disease and insects management. And there's, of course, an interest in evaluating new application methods to establish these controls. So what are the advantages and disadvantages? Ground rigs, there are a lot of pros. You get flexible timing, you get flexible product choice, you can choose your own water and spray quality, corner-to-corner coverage. You can adjust your sprayer settings to fit whatever environment conditions you're encountering. Aerial systems, such as helicopters, they have a higher work rate. The operator is in the air, it's not you, so there's deferred liability. There's no capital investment for the grower, and it's compaction and trample neutral. Back to the field sprayers, what are the problems? It's a lower work rate, and yeah, there's compaction and trample to be concerned about. With aerial systems, maybe they're not available. It's a scheduling concern. You may have limited product choices. Certainly, you're going to have limited water and spray quality choices. They can't be carrying what a field sprayer can carry. And there's a public issue too in some cases. The perception of drift isn't well accepted. And field accessibility, things like tree lines, hydro lines. Helicopters aren't always the best choice. And along comes the drone. The pros are flexible timing, kind of like your own field sprayer. Again, corner to corner, minimal investment, all things considered. It's compaction and trample neutral, and it's exciting. The cons, boy, it's slow. It's the lowest work rate. Sort of like other aerial systems, there's limited water and spray quality choices. In Canada, it may surprise you to know, there are no registered crop protection products, no liquid ones anyway. And I think we can all agree there's still a fundamental lack of understanding in how to use a drone optimally. So that's why we had the study. And we really had two objectives that I want to talk about. We wanted to quantify spray coverage in field corn at 3 depths. And we wanted to do it on targets that were facing up. Those are adaxial surfaces. And the elusive underleaf coverage, the abaxial surface. And we didn't just look at coverage in a generic sense. We looked at it 3 different ways. We did it as residue by indexing the coverage to the percent of the applied rate per acre. What that means is if we sprayed out X amount of product per acre, how much did we find on the target? We also looked at the area covered, just as an overall percentage of the surface covered. And we looked at deposit density, which is how many drops per square centimeter could we detect. We also looked at drift. We wanted to quantify it again as a residue based on percent applied rate. Again, if we sprayed so much per acre, how much traveling at 110 miles an hour. And that was performed with the John Deere rear mount with ExactApply. And in the other field, we used a New Holland front mount system. So, a nice diverse set of ground sprayer application methods in a reasonable volume. It's not incidental, but it is a lesser part of this study. We also explored directlet applications. I'm kind of excited about these drop nozzle systems. They're called belugas. They're built by Agritop. We also did 20 gallon sprayer using this system, traveling at 4.5 miles an hour using Greenleaf's SprayMax 110s. And as you can see, it's quite the car wash when you suspend these in between the corn stalks. We space the nozzle bodies to create uniform coverage. It's a 100% overlap. from the 110s within the silking zone of the plant. That's where we focused. As for the drone, well, they certainly changed quickly. And last year when we did the study, the drone that everyone seemed to be using was the DJI Agris T10, which, even a year later seems kind of small and slow to me. But that was the flavor of the month, and that's what we used. We used AIXRs with a 50 mesh that we had to sort of jimmy into place. We flew 2 meters above the tassel, more on that later, and we used two conditions, 5 gallons per acre and 2 gallons per acre, and that necessitated different speeds and pressures, which again, I'll talk about later. Here's Adrian running a calibration check. We followed good laboratory practices. We established nozzle flow. We confirmed pressure. You can see he's got a gauge mounted there. And as for speed, we used RTK GPS. This was early days when we started, and we really wanted to understand swath. And the reason we want to understand swath is we want to establish the most consistent coverage possible in the most efficient way. But when we started this, our first question was, I wonder how far this drifts, because we have to set up treatment blocks and we don't want overlap. How big should our buffers be? So we went out to the wee hours, filled it up with a fluorescent dye, and performed an initial qualitative drift assessment. Basically, we flew to at different altitudes and different speeds with different tips, and then paraded around in volunteer canola with black lights looking for spray. And it was amazing how far it drifted. And it started to build the edges of the puzzle for us about how far apart these treatments should be. Then we started to dial it in. We performed effective swath analysis using this system that Mark might talk about. This is his swath gobbler system. Receipt paper is laid out perpendicular to the flight path. Some non-toxic dye is put into the drone. We fly it over the receipt paper, and then there's a reel scanner that turns this into a histogram. So, we get an indication of how much spray went where. We also performed something you might be more familiar with. We used water-sensitive paper and did some fly-ins based on Operation Safe. You can see here we've got mounting blocks, water-sensitive paper. You can see the flight path in subset A. We tried to keep it away from, big obstacles like hedgerows, which you can see there. And we ran it between 2 poles, spaced the papers out every half meter under the swath, under the flight path, and then every meter to the left and right. And that gave us this. When you're trying to establish how wide your swath is, I've heard it said it really depends who you ask. It's not the drone or the setting, it's the interpretation. And it is a bit of black magic. So working with Dr. Tom Wolf's calculator that he built in Excel, we plugged in our numbers and attempted to balance the over and underdosing that drones are quite capable of. You can see that it's a rather high and narrow peak on the swath. So, where conventionally we might be concerned with just getting the lowest CV, there's another concern with drones, and that is over and underdosing, because you need so much overlap to fill in those edges. So after multiple passes and multiple techniques, for the 11002s at 3 gallons per acre, we found the sweet spot 2 meters above the tassel, and that effectively gave us a 3 or 3.5 meter effective swath width. Quite a lot of preamble before we've ever sprayed corn. So how did we do it? We built 8-foot high collectors out of PVC pipe, and then through some creative Amazon purchases, I built big chip clip style collectors, and that allowed us to position collectors anywhere we wanted vertically. And we chose to do that at 3 different depths, at the top of the silking region, in the middle, and at the bottom. That's like 2 feet from the top and 2 feet from the ground, and they just sort of span the middle. Now the samplers, we oriented them both facing up and facing down, or adaxial and abaxial. And we alternated left or right between water-sensitive paper and these mylar sheets. Just to give you a sense of scale, we ended up going through over 1,100 water-sensitive papers, over 850 mylar sheets, and we ended up setting up a lot of poles in a lot of corn. Ultimately, we set up 19 3x3 collector arrays, so that's 9 of these poles. We set them up 100 meters into the field and 200 meters into the field. You'll have to forgive me going back and forth between imperial and metric, but I'm Canadian,
and we're mutts when it comes to units. Here's an overhead of how the field was actually arranged. It was a randomized block design. We performed this in 2 fields, and you can see those Ritz cracker, those gray squares, show the 9 poles in an array, set up 100 meters in and 200 meters into the field. For the drones, we set up 60-foot wide treatments, and for the field sprayer, because it was a 120-foot boom, it necessitated at least 120 feet in the treatment block. And it doesn't give a sense of scale here the way I would like, but this is 1,800 feet deep, or 1,150 feet deep, depending on the field. We ran 2 gallons per acre, 5 gallons per acre. We ran 3s, but I haven't included them in the study. Just stuck with the extremes. We had untreated checks. And what I want to show you is we also used our flux collectors, these poles to collect drift. Those are represented by the X's. I'll just highlight those here. I'm not used to using this little highlighter. And it was tricky. Those had to be set up in the downwind direction and just outside the swath, or certainly outside any potential offset for the swath. We didn't want to spray them directly, but we wanted them at ground zero to begin collecting drift. The very first thing I learned, and it was exciting to discover, that I was horribly allergic to corn. I didn't detassel as a kid the way maybe some of you have, and corn rash and allergies made me look like I'd been beaten in a mugging. So thank goodness for Benadryl. I highly recommend it. I was dressed up in plastic for this entire week, which was oh so comfortable in 30 degrees Celsius weather. Here's a peek at the horizontal flux poles. These are extendable poles, almost like a graphite fishing rod, if you can imagine snapping this thing out. They were positioned, as I said, just downwind and slightly beyond the RPAS swath edge. And we set these up at 3 different distances parallel with the treatment block. Maybe, I think they were 50 meters apart. I'll let Mark say that. I can't remember. You can see here the arrows show the flags at the top, this flagging tape, just to give us a gut check to ensure that the wind was still moving in the right direction. We wanted them exactly downwind where possible. And those had to be carried about 150, 200 meters into the field. They were strung with this braided thread. Again, if you want to ask Mark about it, this is his baby. And they're stretched, boiled, and bleached, or whatever he does to ensure they're absolutely clean before they're run up the poles like a flagpole. The spray intercepts these strings at different depths. And the beauty of this system is, unlike ground deposition, anything that sort of stays airborne, never lands downwind, at least not immediately, will be intercepted by these strings. We feel they give a much more accurate representation of downwind drift. Of course, we had to look at data from weather conditions, so field-specific weather data was collected at about nozzle height using these Kestrel systems. Not Mark's favorite, but we didn't have cup anemometers. And we supplemented that information using field-level weather summary reports that were local to the field owned by the growers. So I think we had a fairly good indication of wind speed and direction and pressure and all those good things. Here's Adrian mounted dramatically aboard his truck. We applied formulated product at 8 ounces per acre. It's a fungicide. It was part of the study. I won't mention it. But the important part for us is we also include a tracer dye. PTSA is fairly standard in spray drift calculations. Here you can see the drone flying over the corn. The reason I have this slide is to show that the corn was visibly displaced by the downwash. The downwash is the air that the drone produces. Unlike planes or even helicopters that are traveling at spraying speed, the RPAS always creates a downwash, and we wondered if this would help drive the spray into the corn. What's interesting to note is when you change travel speed, you change the duration that air is focused on the corn. This is called dwell time. So the slower it moves, the more opportunity for that air to be focused on one spot. And the faster it moves, the less it's focused on one spot. This will play a role later on. After the passes, the samplers were collected into uniquely coated bags. Mark would cut these down 1 meter at a time so that we got a cross-section by altitude, and they were slapped into coolers as soon as possible, even though the PTSA is very shelf stable. All the water-sensitive papers and mylars were collected, each one stuffed into a uniquely coated bag. Boy, we agonized over that. The papers themselves were characterized using a drop scope, which just takes a digital image of the paper and spits out a deposit count per square centimeter and calculates the percent of the surface covered. Back in the day when I used flatbed scanners and it took a lifetime to scan these, this is just a superior method. You may be wondering why we bothered to look at coverage so many different ways. I'll just focus on the water-sensitive paper for a moment. The reason we cared about percent surface covered and the number of drops per square centimeter can be kind of summed up by this battleship metaphor. Over here in A, we've covered 10% of this surface. Let's pretend those are droplets on a leaf. So if we say, hey, I got 10% coverage, and you think that's not bad, is this really good coverage? Because all your droplets are smushed into this top left quadrant. You've effectively missed 3/4 of your target, even though you got 10% coverage. Now that same 10% coverage in image B shows the importance of describing how the droplets or deposits are distributed over the surface. Here's the same 10% coverage, but I think you'll agree this looks like you have a better shot at intercepting a pest, either an asc spore for disease or maybe a sessile insect. Basically, your odds of contact go up. And all C shows is if you do repeated applications and you have a good distribution, the odds of hitting the same spot twice are fairly low. And it's why we like to spray fungicides, for example, as the leaf grows or after weather conditions conspire to reduce residual. We like to spray them over and over, and you end up with a nice overall leaf coverage. As for the PTSA, again, Mark can speak to this. This is what he did in his lab. All those samples were sent back, and the amount of tracer was washed off the strings or washed off the Mylar cards, and we did a calculation based on how much we applied per acre and worked out a percentage of how much we recovered. So what did we find? Well, the first thing we found was that water-sensitive paper measurements of both the percent area covered and deposit density, when compared to how much residue we rinsed off, revealed similar coverage patterns. So while these might appear to be redundant methods of detecting coverage, one is a heck of a lot easier to use than the other and can be done quickly and more cheaply. So it was nice to know that the two of them agreed with one another. Now, when I say that, I mean both RPAS and overhead broadcast from the field sprayer both produce similar deposition patterns within the corn canopy. There was a negative linear relationship between the amount of coverage and the sampler depth. You got a lot at the top, you got less in the middle, and you got far less at the bottom. In big canopies, this generally isn't a linear relationship. Say if you were spraying sideways into an apple tree, it tends to decay logarithmically or more. But in this case, it was linear and pretty darn tight at 0.997 R squared. Here it is graphed out. I'm only mentioning the collectors that were facing up, the adaxial collectors, because we sure didn't see much on the ones facing down. We could have saved a lot of collectors and effort, but I guess we did prove something by finding such poor coverage on the underleaf side. More about that in a second. On your left, this part of the histogram, there's the average percent area covered, that's the papers, or percent applied, that's the Mylars. Mylars are blue, water-sensitive paper is orange, and you can see that decay at the top, middle, and bottom is pretty linear for both systems. This is 2 gallons per acre, and this is 5. So it didn't matter how much volume you sprayed, that coverage pattern remained the same. Now, it's still kind of hard to compare Mylar to papers because they're different methods. So if we make the assumption that the paper at the very top of the corn facing up is kind of the best you're ever going to do, if we call that 100%, we can index everything to that position, which we did. So assuming the top is the best you're going to do for both collectors, you begin to see just how lockstep they actually are. So there's the first takeaway. If you want to do work with water-sensitive paper to confirm your coverage, it's a pretty good option to do that. And if someone says, hey, residue is better, yeah, maybe, but given the cost and the effort, it's nice to have those two options. The second result, we found that overall coverage shared a direct relationship with the volume for both the drone and the overhead broadcast. And I guess this is no surprise to everyone. The more volume you use, the better the coverage. Now, there's diminishing return on that. If you go up to 150 gallons per acre, if you could ever do that, it's not as if you're going to see that much more coverage versus say 100 gallons per acre. It's as in total, it just sort of levels off. There are big gains from 5 to 10 to 15 to 20 gallons per acre, but 50 to 100 gallons per acre, probably not worth the water. I'll get into some detail here. For the drones specifically, spray coverage was significantly reduced when we sprayed at 2 gallons an acre versus 5. And by that, I mean all 3 different ways of coverage, like minus 58% less coverage based on the mylars, like almost 60% based on average area, and like almost 75% based on deposits per square centimeter. So no matter how you slice it, using less water meant considerably less coverage. And we graphed this out for those who are visual people. Here's the 16.67 gallons per acre applied by broadcast. Here's the average coverage we saw on the top collector facing up, a sad nothing on the top collector facing down. Then we saw how much coverage in the middle, nothing facing down. And at the very bottom of the corn canopy, there's the coverage again, and nothing facing down. I'm just going to skip over the directed for a moment. That's the drop arms. And here's the drone at 2 gallons per acre and at 5 gallons per acre. So if we were looking at this strictly as the percent area covered, you could see that the 5 gallons per acre in the drone did better than the 2. But wow, compared to overhead broadcast, kind of sad. This surprised us. There's the 20 gallons per acre with the car wash kind of nozzles. And look, we actually did see coverage on the underside because the spray is directed kind of upward from inside the canopy. So it's on the right vector to hit that surface. But it didn't look to cover any more area than even maybe the drone at 5 gallons per acre, which is kind of promising because we know we get great efficacy from this system. I'll talk about that more in a moment because, it baffled us at this point. More results. The directed applications, those drop arms, I should mention they made a pretty fine droplet. Those were XR tips, so those are fine medium at best. And they didn't have to travel very far, just a few inches from inside the canopy. While it did kind of crummy as far as overall percent coverage, it really shone when we started counting droplets. Here's the same histogram again, but not percent coverage, rather counts per square centimeter. The broadcast doesn't look as well, does it? Because great big droplets means fewer droplets. In fact, it's starting to look a lot like the 5 gallons per acre when you look at how many drops were actually produced. For a contact product, that may play well for the drone. The 2, high error and, just not enough droplets to work with. But look at the directed. That kicked butt. That is a lot of drops per square centimeter. And for a contact product, that may trump the area covered. We're getting near the end. Conversely, let's talk about drift. Our past spray drift was significantly increased in the 2 gallon per acre treatment versus the 5. So coverage suffered for 2 gallons per acre, but drift went up. If you took every meter of that horizontal flux system and graphed it out, which we've done here, and this is pretty much the scale. There's the drone 2 meters over the tassel. There's the corn about the right height relative to the drone. And here would be sort of the flux pole at 8 meters high. The blue is the amount of drift we intercepted as percent of the applied rate. Almost 2% of everything sprayed ended up about 1 meter off the ground for 2 gallons per acre. And you can just look at this curve, look at the blue curve, and the overall area under that curve gives us a sense of how much volume left the system. Look at 5 gallons per acre, the red. It's less. So even though we sprayed more, we drifted less. Why? We think it was because of the travel speed. In order to get to 5 gallons per acre, we had to slow down. So we flew at 3.3 meters per second. And there was also a change in pressure there, but we won't get into that. To get to 2 gallons per acre, we pretty much had to drop the pedal and fly at 7 meters per second. And when you do that, the drone tips forward. That increases the proportion of spray that's directed back and out rather than down into the corn. So when that happens, any of the finer droplets in the spray just sort of run out of energy and they end up hovering in the air with gravity not being enough to pull them down. and they get blown off course. So that kind of explains why we had poorer coverage and higher drift at a lower volume. There weren't many droplets, and they were being aimed in the wrong direction. Now, we did this in 2 fields, so you have to look to see, is there any difference between one field and the other? There shouldn't be. It was the same corn variety planted the same way, and within a few days, the weather we thought would be near enough. But we did see a field effect. There was a significant difference between field 1 and field 2. Field 2 had lower overall coverage and higher drift, and it didn't matter if we sprayed 2 or 5 gallons per acre. So what was happening there? Well, I'll just get a little more specific. Compared to field 1, the average coverage in field 2 was like 30% less at 2 gallons per acre and like 40% less at 5. And drift was up almost 75%. So these are big numbers. This wasn't a small difference. So let's do this a little differently. Let's just lump together all the drift we saw in field 1 and all the drift we saw in field 2. That's what you see here. The red is field 2. Look at that drift. It's so much more than field 1. So what the heck happened? Well, like I said, the crops were at the same stage of development, same variety, same planting architecture. The ground was flat. There were, no trees around. So what was the difference? It was the wind. We got near the end of the trial, and we've all been there. The wind picks up, and we had to get it done. The average wind speed in field 1 was almost 7 kilometers an hour, pretty reasonable. But on those last couple days, we were up to like 19 kilometers an hour in field 2. That's 3 times as high. So it had to be the wind. So here's the take home. You've all been very patient. For the use cases explored in this study, that is like the specific parameters that we used, we'll say that lower volumes and higher travel speeds are not advisable for drones. And, that's just made even worse in high wind conditions. Also, for those who want to establish a way to look at coverage and be confident in it, both water-sensitive paper and residue samplers together form a complete coverage picture, especially when you're using contact products in finer droplet sizes. If you were to just rinse off a Mylar sheet and say, oh, look, I got 1% of everything I applied here, the same way looking at percent coverage, you don't know how that spray was distributed over the target. You really do need to look at deposit density. And these 3 things together give a very complete picture. But if you're in a bind and you just want to get her done, water-sensitive paper is a viable method. It leads us to future work, and given that this was done last year, we're still hoping to do some of it this year. We would really like to separate travel speed, ambient wind speed, and volume. And that would help clarify their relative influence both on drift and coverage. Sadly, when you want a higher volume, you kind of have to slow down to do it. So you mush those 2 variables together, and it's hard to figure out which one caused the difference. Shameless plug, Mark and I wrote a book. This is Air Blast 101. As drones become more and more prevalent, I think we're beginning to understand that, they're not like any other application system, save one, and that's an air blast sprayer. They use air, and how the droplets behave in that air and how they're driven into the crop and how it responds to air, we think is as big a variable as anything else. So anyone that sees these as flying boom sprayers would be mistaken. And if you're curious to learn more about how air and spray and crops behave together, then by all means, go to sprayers101.com and grab a free copy of our book. If you're old school and prefer print, that's available too. And that website is Sprayers 101, something that I put together and host with Dr. Tom Wolf out of Saskatchewan, Canada. And it's kind of everything you never wanted to know about spraying. So we invite you to go there and take in anything you like. We've got lots of videos, lots of downloadables, lots of authors from all over the world. And we've done our best to make it easy to navigate through a search engine. And it's completely free to you. And we don't take money from anyone except grower organizations. We're not selling anything. So it's an unbiased opinion. And with that, thank you very much. I hope you enjoy the rest of your conference, and I hope that you have lots of hard questions for Mark. Thanks, Steve. Thank you, everybody. Hello.
Well, all right, Mark.
All right, and thanks to
Uh-huh.
everybody yeah, thanks to Jason for recording that, because I did not have time this week. And the 6 of you who have hung on to the to the naked end here, the bitter end. So the one thing I wanted to, I don't know if there's any questions in the chat here or not, but the one thing I wanted to point out is how we present the data. Jason kept saying percent of applied. And what we always do is we figure it doesn't really matter how much dye or how much water we put out. We always index the dye as a surrogate for the chemical. You're always going to put the same quantity of fungicide per acre, whether or not you put it in 2, 3, 4, 5 gallons per acre. So then we index that to a percent applied and present the data that way. That makes it easier to really understand where you put your chemical.
Mhm.
And if you're just looking at it in gallons per acre and coverage, we always index. So whatever the total gallons per, say we were going to put 2 gallons per acre, we figure out whatever the residue would be for that to have theoretical 100% deposition. And then we compare everything. And that makes it really, really easy to compare lots of different numbers and have a meaningful comparison.
Well, Mark, when you say percentage of applied,
Mhm.
I know you measure the dye caught by the strain, on the sampler, and you know the diameter of those strains, so you can calculate an area as well. So what's gonna be the base that concentration you found on the strain to be compared to? What's that base concentration or the base amount you calculate the percentage of applied?
That's what we do. Is so we take that percent of applied. We assume, okay, we applied 2 gallons per acre, 4 ounces per acre, whatever, and what that nanograms per square centimeter on the ground if there was no corn.
Oh, gotcha. Okay,
And
so
then I just assume that the ground tipped up 90 degrees to the side. It's a little bit of a fake number, but it's very comparable.
Yeah, I got you. So it's a nanogram per square centimeter. It's the
Yep.
same unit I use, but you use a flat ground to get your theoretical baseline.
Yep.
Yeah,
And
gotcha.
and then we're working on it right now. Can we do like downwind deposition and integrate that curve to
Mhm.
figure out what the total mass loss across that string is? We think we probably can. We just haven't actually got that math done yet.
I
Jason,
think, yeah, I think that's a good way to describe our data, because theoretically, if we have zero wind, all of the nanogram you sprayed is supposed to go straight into the canopy. And then, if you collect all the leaves out there, you'll be able to see a vertical distribution of the dye, which if you adds up all of those concentrations together, it should have match that theoretical baseline number, that nanogram per square centimeter using the flat ground.
Yeah, and Jason and I argued about this, because we did a stratified study. I don't know if I got video or not, so you can see my hand motion. Nope, okay, you can't see my video. Okay, but I'm very expressive with my hands. But we didn't pull a few whole corn stalks and just wash them to see, that would be what you'd have to do a mass balance. And I personally don't like to do leaf washes because I don't know what my recoveries are on them. You have to assume that you recovered all the dye, or that every leaf you get the same percentage of the dye coming off of it. But in my prior experience, that's not an assumption I can always make. So that's one of the reasons why we collected our dye on Mylar. It's not a leaf, but it's a sampler that we can compare, and we know that we can get all the dye off of it.
Yeah, the other issue with collecting the leaf is every leaf has a different size. So that actually adds a lot of extra work. Last year when we got a whole leaf off, we have to scan every single leaf to get the leaf area size in terms of square centimeter. That was a lot of work. And also, I have another question. When you spray 2 versus 5 GPA, Did you mix that dye at a different concentration so you deliver same amount of active ingredient per acre?
Yes,
Ah.
so the 2% or the 2-gallon coverage had more dye per gallon in it. It had
Mhm.
the same amount of dye per acre, and then we went back and adjusted that for the calculation
That's good, yeah.
in the end.
So you
It
mix
doesn't really matter.
like the chemical.
We could go, some studies we do a master batch and then just adjust it that way. This one, we mixed every batch uniquely. And we actually take a tank sample with every, we take a tank sample, first tank and last tank with every plot. Those were enormous plots. They
Mhm.
were, 100 meters by 1,000 meters long, because they wanted to get harvest data out of it as well. So I mean, spraying 5 gallons to the acre took over, I think it took 24 or 25 minutes to spray those plots, because yeah, they were enormous plots.
Mhm.
Actually,
Yeah.
I'm sorry, it was 100 by 1,000, because they were 1 hectare plots.
Yeah.
Yes, 2.5 acre plots.
Yeah, that's what we did. We have a tank sample after we drain the tank on all airplanes and all the drone treatments, because that concentration has never been the same.
Yeah.
You
It's never the
have to use
same. The other
that.
thing that I learned, a little trick that I learned, is I used to freeze those darn things. And because of your tank studies, when you concentrate the chemical, sometimes you wind up getting interactions when you freeze. Because you have super concentrated active as the ice crystals form. So when we take our tank samples, we mix it 50% with denatured alcohol, and then it won't freeze. And also you have no bacterial breakdown. So that sample then becomes stable in the freezer forever.
Yeah.
And that's allowed us to get much better fluorescence curves. A little more work, but you get good data.
We typically just put them in not a hard freezer, but just put in the fridge and analyze them in the next couple of days.
Yeah,
So,
that works. If you can do that, that works great. I
yeah,
would
yeah,
oftentimes
we never let it stay very long in water.
Yeah.
Uh,
But anyway, that's really in the weeds for collecting data collection.
yeah, yeah, because the 2 versus 5 GPA, and also the field 1 versus field 2, which field 2 was sprayed with 3 times more wind.
Oh
I
yeah,
thought
it was
the
blowing
most,
like crazy.
interesting data. Yeah.
And we were half of our reps in field 1 were in inversions. They were evening, the inversion was setting up. There was almost, it was stable air.
Mhm. Yeah.
For the study, we weren't allowed to go under 3 mile, under 3 mile an hour wind. They were trying to get us to follow label recommendations, but we wound up scrubbing 2 or 3 reps because the wind just dropped halfway through the rep. I was like, okay,
Oh yeah.
no wind. Guess we'll throw all those away.
Yeah.
But
Well, no wind doesn't necessarily mean there's a temperature inversion. So
where we are, it does.
it does. Okay.
Yeah, it absolutely does. Yeah, I know. I understand your meteorology is different down there, but up in the in Mediterranean climates where we're at, it always pretty much always means an inversion. And that night, I know for a fact it was an invert. Those nights they were. But
Yeah.
there's a comment on a publication. Jason and I are working on a publication. I should say Jason's working on a publication. I never get it done. And they were, I think, the person who asked about the XR 110 15s, I think that is what we were using on that. They were XRs.
XR, but it was 110.02 or 15. I forgot.
I don't know if it was a 15 or an 02.
Oh yeah, either a 15 or 2.
Yeah.
But
I didn't nozzle it. I left that to Adrian. This
Hmm.
Yeah, another thing, if people can still go back and see your drone seminar from when was it? It was March that you did the last one. Bear presented this data from this study, including a lot of spectral data. That was Matt Verkane's presentation.
Yeah, true.
That was this data set. So if that's still available online, that was an interesting piece of efficacy data that we didn't present here. Drones with a boom versus boomless drones. Booms, generally speaking, to me, are no different than ground sprayers. That high cycle sprayer you saw can spray with a boom 10 feet in the air. Once you get the nozzles outside the downwash, you have very little benefit from your release height is essentially whatever the boom height is. There's some advantage still. Well, you can get it caught up in the wake out behind it and get some downward movement, but you're really, once you're outside the downwash, you're really an awful lot more like a boom sprayer. And the drift that we've seen from that is typical to what you would get if you put your numbers for those application rates and speeds in AgDisp. If you run AgDisp and you put the nozzles at 10 feet in the air with all the application parameters, you'll get a drift number, and it's not that different than what we see for boomed. You know, the boomed drones have gone out of style to a large degree. You know, the ones that were reaching out 2-3 meters past the downwash.
That's a safety hazard.
Then there are other issues around that, and the pumps can't keep up with the swath width and things like that. So, and there's a lot of assumptions about nozzle overlap that don't necessarily work on those. So you still need to swath it. So that's yeah, I have to say I'm kind of with Steve. I like the rotary atomizers when they're used right. I think they're being needlessly penalized right now because they don't conform to the droplet size the S327 or 527.3 or sorry 572.3, get the right number from ASABE. They don't conform to that standard, so they get penalized, and the label recommendations ask for far too coarse a droplet. But I was critical of that DJI rotary atomizer, and it's working with Steve and a few other people since, it does a nice job. It makes a lot of droplets, and really, if you can keep the droplets in the downwash, those fine droplets are not the enemy. But you got to keep them in the downwash and get them sequestered in the canopy. And I think that's some of what you saw, Steve, with those middle application rates where you got really heavy coverage in the middle of the canopy. You push a cloud of mist into the canopy. It's no longer a drift risk. It's sequestered in the canopy. Those little droplets will ping pong around for the next 2 or 3 seconds until they deposit somewhere. And that's probably going to be around the ear leaf, because that's kind of the middle of the canopy.
Yeah. Well, and also you can spray a little thicker tank mix with the rotary atomizer versus the nozzle drone, and that's
Amen.
Too. That's a benefit.
I hate 015s and 02s. I mean, if you got to use them, but most drones do not have the filtration to be able to operate those size nozzles.
Mm-hmm.
And honestly, most humans don't have good enough eyesight to know when they're bad until they're so bad.
Yep.
Yeah.
The orifice is so small, they get clogged up real easy.
And rotary atomizers will atomize mayonnaise if you can pump it. And you're running DJIs, but I mean, heck, when you go over to the XAG, they've even got a peristaltic pump in there, so you could literally put mayonnaise in the tank and it would pump it. And that's a huge operational advantage that you just can't overestimate. Yeah,
that's a benefit for sure.
But the one thing I do want to say, and Steve alluded to it too, that you need to be a little higher and a little faster, it looks like, with the rotary atomizers to get that pattern spread out a little bit more. If you're too low and too slow, you can have a really M-shaped deposition pattern because they'll pound the ground and not spread out. Mike Rinke has about 150 swaths already scanned. We're going to have to go back and do another program like this and just present Mike's data, because it's crazy. It's now, granted, most of his data was focused on, and this is not out there yet. I'm just kind of alluding for the folks that are left on the call here. I'm alluding to data you can't see yet, but we were kind of setting our minimum threshold at 2% coverage, and that makes for a pretty narrow swath, as you showed. Most of the swaths just aren't that much coverage. And Mike is focusing more on horticultural crops, so he's looking for higher coverages. But at really low speeds with the T40, you'll see a definite miss in the middle where it just so flying it faster and letting that wake bust apart the spray plume seems to help.
Well, for a big heavy drone, and in future you're gonna have stuff bigger than T40. If you let it fly too slow and still using a full flow rate, considering or assuming the flow rate will be even higher, I think the risk is if your canopy is not thick enough, it's not strong enough to retain those droplets, you might can blow through that canopy and just waste your chemical on the ground underneath that canopy.
No doubt. Or you'll bounce it back out of the canopy.
Well, yeah, if that happens,
We
if
do it in grapes. If you hover it real slow, we blew the vines right off, or the shoots right off the vines.
you damage cause you
Yeah.
cause physical damage.
I
So
was
that's
surprised.
what
I didn't think we would. But one of the trials we did was in late June when the vines are still quite tender.
Oh yeah.
And, yeah, especially you fly past 2 or 3 times, you got to be careful. You're right.
So this go back to the point I make. You really have to consider the canopy characteristics, the canopy thickness when you design your fly path, fly parameter, all of those to make sure you blow just right amount of the product into that canopy, not too shallow, but not too deep either.
So EO, you're not going to like my answer to any possibility of standardizing so many variables we have in spray drone designs. No, there isn't.
No.
And here's the reality. A ground sprayer has droplet size distribution, boom height, travel speed, and wind are your primary variables. They don't really change. With the drone, we've got a much more variable travel speed. You've got pitch, roll, and yaw. You've got downwash that we don't even know how to measure yet and quantify. And that will change dynamically with the load. An empty tank will have very different downwash from a and then into and against the wind, because the downwash is another variable. Now we're talking about an 8 to 10 variable system. And
also,
you heard me make this joke before.
Don't forget your famous point. Every flight you make with a drone is a variable weight application.
Yeah.
Good luck with that. You can't standardize that.
And that's a variable you're not going to standardize, but I really have to say I like that the industry's gone to these 4-arm rotors, because you're not going to have as much variation as you go. Like the octocopters earlier on, if you had a quartering in wind, heck, the front 3, the 3 rotors going into the wind weren't even turning, because the drone would flip over. So these X-shaped ones, I think, give much more, or the 2 rotors, like on the XAG, give much more uniform downwash, because they don't have to move energy around as much to stay stable. And I think that's been an improvement.
Yeah.
But until we all have a quantum computer on our iWatch, you're gonna have to swath, for the weather you're dealing with and your application situations. That's one of the reasons we work so hard. Whether or not you buy a swath gobbler or not, I don't really care. Obviously I want you to buy one, but what I really want you to do is lay the paper down on the ground, do the dye sprays. It doesn't take long. Literally, while you're setting up the rest of the field, you could go and swath your drone. Every time you change your use case, you should be swathing.
I think in the foreseeable future, this may or may not happen by the time I retire. We're still gonna have to use the paper on the ground, the collector on the ground, and also put the water sensitive paper and the collector inside the canopy to do vertical sample collection, doing vertical and lateral, 2D, 3D to quantify and actually get some idea of how well the coverage is when we work with a new canopy. every canopy is different, every crop. So
And can I make a shameless plug here, Steve?
yeah.
So for the folks that stayed all the way through this, thank you again. If you want to know more about the plans for building the boards, we give those away free. Heck, you can use any dye you want. Steve used rhodamine, which is great. You can use beet juice, you can use grape juice. We supply FD&C blue #1, which is blue M&Ms. I like it for lots of reasons. But if you go to betterfieldstudies.com, we've got all the information you need. There's a lot of free stuff on there. And if you actually want to buy some dye and paper from us and you don't want to go track it down yourself, we sell it. But I'm really want to be an advocate. We're trying really hard to teach people how to do it themselves. You don't have to spend money with us. But once you swath a few times, you'll really find it empowering. I mean, Steve, you see this every day on your forums on Facebook, and people that what swath should I be spraying? How does anybody know? And if they took their answer from a Facebook forum, how do they know? I mean, what kind of blithe confidence is that? So
Yep. All right. We have to call off of this thing. Otherwise, the recording will even be too long.
yeah, it's getting really long. It's again, yeah, this has been good, Steve. Thanks for inviting.
Oh yes, sir. Thank you for your time very much. It's been 2.5 hours. I feel like all this type of technical training, we said it will be done by 2 hours. Usually it run at least 30, 45 minutes longer, but yeah, hope the information you received is useful for your operation, and also I will send out a email with the recording link. You can click on it and just watch it. Probably will send out the recording link just using the Zoom as well. That's the quickest way. Until I have time to edit the video. That link should be good for at least 3 months. It'll take you to the Zoom platform and you can watch this thing directly on Zoom's webpage. If you have questions, for folks watching the recording, if you have questions, you can reply the email that I send out with the Zoom with the recording link. I will copy Mark on that email. I'm sure he wouldn't mind answer a few questions. So after you watch the recording, if you got questions, just click reply to all. So both of us can get your question and we can reply your question via the email. And again, appreciate all the 6 folks still held until real late. You guys are awesome. I'm sure you guys will be top notch or already be the top notch applicator if you can handle this much of technical information for 2.5 hour torture, and still haven't got brain dead
and ask great questions.
By now. Yeah, I still ask a question. So this has been awesome. All right, so we'll continue the effort. I'm not sure if I have another training this year or not, but you probably will hear from me about the next spray drone end user conference soon. We're gonna start the event organization or start a organizing committee in the fall and just lay out the work we need to do. So next year we'll do in person combined with hybrid. So we'll offer plenty opportunities for folks to calm down and interact with people, because I believe networking is very important, so it was just going to be bigger and better than the previous one, which is 100% on Zoom. So all right, at the end, I want to wish everyone a great night, and also hope y'all have a great rest of the season. I know most of the corn fungicide is completed by then, but maybe still folks are busy with field operation. Down here, we still want to spray cover crop and spray cotton defoliants, and I still got some cotton PGR need to be sprayed. So down here in the south, we're still quite busy. So.
Well, and up here, corn's just ramping up right now. So,
yep, there may be some fungicides still need to be sprayed, over there where you at, but all right. Just want to say thanks again. Also, Mark, thank you for your time and support as always. You have been very helpful for all of us. So. So just want to say thank you.
Likewise, like, yeah, it's great what you do here. So it would be easy not to do what you do here. And yeah.
Yes, sir. All right. Also thanks to Jason, although he cannot hear us. His presentation was awesome. It was awesome.
He always does a great job.
Yes, sir. All right. Hope you see all of y'all soon, and just wish best of luck with the remaining of the season. Hope everyone had a really good summer as well. All right. Take it easy.
Good night, Steve.
Yeah. Good night.